Hello, my name is Kailash Bhosle. I am from Sanjeevani College of Engineering, Kopargaon. In this session, we are going to study about the unit number 6, principal planes and stresses. For this unit, we have referred on these textbooks as well as reference books. At the end of the session, the learners will be able to derive the 3D stress equation. So, in every component, when we apply the load, the stresses are developed, and this is the state of the stress in the 3D components. The most general state of the stress at any point may be represented by 6 components. So when you apply a load on a body, then the stresses are developed in the all 6 directions: sigma x, sigma y, sigma z, and the shear stresses are tau xy, tau yz, and tau xz. So when the load is applied along the direction of x, the stresses will be developed sigma x. Along the y direction, tau xy will be shear stress. Along the z direction, on this plane, tau xz will be the shear stress. Similarly, when we apply the load on this plane, then the sigma y is the shear stress which is normal to this plane. Then along the x direction, tau yx, and along the z direction, tau yz is the shear stress. Then when we apply the load along this z direction, sigma z is the normal stress. Then along the x direction, tau xz the shear stress, and tau yz is the shear stress along the y direction. There are two stresses. One is the normal stress and the shear stress. The substrate identifies the phase on which the normal stress acts. Tension is positive and compression is negative. And the shear stress, it has two subscripts. The first subscript denotes the phase on which the stress acts, and the second subscript denotes the direction on that phase. A shear stress is positive if it acts on the positive phase, and the positive direction of it acts in a negative phase and negative direction. Then for the static equilibrium, tau xy will be equal to tau yx, and tau xz will be equal to tau zx, and tau zy equal to tau yz, resulting in the 6 independent scalar quantities. These 6 scalar can be arranged in the 3x3 matrix, and this will give the stress tensor. So we can write down the values: sigma x, sigma y, sigma z, and the remaining shear stresses. The sign convention for the stress element is that a positive force on a positive phase on or a negative force on a negative phase is positive. All other are negative. The stress state is a second order tensor since it is quantity associated with 2 directions. Same state of stress is represented by a different set of components if the axes are rotated. There is a special set of components when axes are rotated, where all the shear components are 0. So that will be principal stresses. So at one plane, we have to find out the what is the value of maximum major principal stress and the minor principal stress. So sigma 1 and sigma 2 are the 2 principal stresses. Maximum, one will be the maximum, another will be minimum, and the sigma 3 will be in between sigma 1 and sigma 2 values. A property of a symmetric tensor is that there exists an orthogonal set of axes 1, 2, 3, which are called as principal axes, with respect to which the tensor elements are all 0 except for on the diagonal. In the matrix notation, the transformation is known as eigenvalues. The principal stresses are the new axis coordinate system. The angles between the old axis and the new axis are known as eigenvectors. Next is the plane stress. The state of the stress in which two faces of the cubic element are free of stress. For the illustration example, the state of the stress is defined by it is the part where the shear stress will be zero. The shear stress will be considered positive when a pair of shear stress acting on positive sides of the element produce a counterclockwise torque. So this is one shear stress acting on this side, and this is when they are creating the anti-clockwise torque, then it is considered as a positive one. Then the stresses on the inclined sections, knowing the normal and shear stresses acting in the element denoted by the xy axis, we will calculate the normal and shear stresses acting in the element denoted by axis x1 y1. Suppose that on this plane we have to find out what is the normal stress and the shear stress. So we can find out the result value and then transformation equation for the plane stress. So sigma x1 will be equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos of 2 theta plus tau xy sin of 2 theta. Sigma y1 is sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos of 2 theta plus minus tau xy sin of 2 theta. And tau x1 y1 will be equal to minus sigma x minus sigma y by 2 sin of 2 theta plus tau xy cos of 2 theta. So we'll see the cases when we apply the load along only one direction, uniaxial stress along only one direction. Then what is the value sigma x minus sigma y? So in that case the other value sigma y will be 0, tau xy and tau yx will be 0. And after that we can get the value of sigma x1 and tau x1 y1. Similarly, when we have the pure shear, this is the case. In that case, sigma, we have to put the sigma x and sigma y equal to 0 in that transformation equation, and then we can find out the sigma x1 and tau x1 y1. Similarly, biaxial stress, when we apply the load along the two directions x and y, in that case the other third component tau xy is 0. So when you put that the tau xy is 0 in that stress transformation equation, you can get the sigma x1 and tau x1 values. Then next is principal stresses and maximum shear stresses. The sum of the normal stresses acting on the perpendicular faces of plane stress elements is constant and independent of the angle theta. As we change the angle theta, there will be maximum and minimum normal and shear stresses that are needed for the design purposes. The maximum and minimum normal stresses are known as the principal stresses. These stresses are found by taking the derivative of sigma x1 with respect to theta and setting equal to 0. So these are the principal stresses. One will be the maximum, another will be the minimum, major and minor. And then we have to find out the maximum shear stress. The location of the angle for the maximum shear stress is obtained by taking the derivative of tau x1 y1 with respect to theta and setting to equal to 0. So we can get the value of tau x1 y1 equal to sigma x minus sigma y by 2 sin of 2 theta plus tau xy cos of 2 theta. Similarly, we can find out the tan 2 theta of the plane equal to tau xy upon sigma x minus sigma y by 2. The planes for maximum shear stress occur at 45 degree to the principal planes. The plane of the maximum positive shear stress tau max is defined by the angle theta s1 for which the following equations apply. So tan of 2 theta s will be equal to sigma x minus sigma y by 2 to tau xy. So that will be equal to 1 upon tan to theta p. And tau max will be equal to under root of sigma x minus sigma y by 2 whole bracket square plus tau xy square.